Hey everyone, my name is Franco. I am a product specialist at Databricks. I focus on Databricks SQL. I'm joined here today with some awesome fellows from Databricks, Dillon, Bostwick, who is a senior solutions architect, and Shannon Barrow, who is also a senior solutions architect at Databricks. We're here to talk to you about how to be so fresh and so clean and how to make real-time data warehouses on Lakehouse. And we're going to get into the nitty-gritty detail here. You've heard a lot about these awesome product features that have come out that enable this stuff. But we're going to show you how to actually build them. And Shannon has a long list of learnings that he's had from implementing this that we're going to share with you. And we're also going to be available for Q&A afterwards. So if you want to know how the sausage is made, please come ask us. All right. What is a data platform? Like, what are the components? And essentially, I try to break this down. Essentially, when you're trying to build a data platform, you need three components. You need an ETL layer. You have data in source systems, or files. You need to get it out. You need to extract. You need to transform that data into some type of data model that users can use. You need a storage layer. You have to persist all of this data that you get out of source systems or files. So you need a storage layer. Traditionally, you've called this a warehouse, then came a data lake, and now we're talking about this Lakehouse thing. These are all the same thing when you look at it. It's a persistence layer, right? We need to store these files as objects somewhere, and we do an object store. We refer to this as Delta Lake because Delta provides ACID transactions on a data lake, and what gives us that warehousing ability on a data lake. And finally, you need to serve up that data to your users. All of those BI applications and reports and dashboards, or even any type of connectivity. You heard today that we're launching Node.js and Go as well, and a REST API. So all types of serving. I have users, I have applications that need to build things, I need to serve up that data. So this is a data platform. Essentially, we have Delta Live tables that can give you scalable ETL, simple scalable ETL. We have Delta Lake and Databricks SQL to help you build the data platform of the future. So let's break it down. What is data warehousing? When you break it down at its core, right? So those core components that we talked about. Essentially, as we've seen data warehousing mature over the decades, it's a pretty old technology. It's 30, almost 40 years old at this point. It's basically ETL or ELT with query serving. And there are a plethora of vendors that will sell you parts of this system. Right? Traditionally, you had data warehouses. They came out in the 90s, late 80s, early 90s, and they were essentially the way that you would put all of your data so that you could serve them up to for reports. Essentially, what they found was that compute at the time wasn't powerful enough to give the users answers to their data during the day. So there were these really smart database researchers that came together and they said, what if we process the data overnight? And out came batch processing. But you needed to organize that data, and out came all these data modeling technologies, and Inman and Kimball and Data Vault and everyone that's come out since then to help you organize your data. But essentially, you needed to extract the data, you needed to transform this data through layers, and then serve it up to your users. There's this other paradigm that is being used called ELT, and how I define that, and how most of us define that, I've actually had 3 conversations today about people talking about these different things, is when you just take the data from the systems, you load it, you push it all into a warehouse, and then you do your transformations in the warehouse. You know, you bought tools in the past couple decades like Informatica, Ab Initio, Talend, and others that saved you that premium warehouse compute so that you didn't have to pay premium warehouse compute for all your transformations. Why nowadays you have prominent warehouse vendors telling you to do ELT, again, when we know that they're not efficient at it, I don't know. But this is basically what we see as data platforms being offered and what they do at their core components. But when we are practicing in industry, so I come from field engineering, I am a product specialist now, but I actually helped customers build these things in the field for the past 3 years. And I can tell you, Shannon and Dillon will tell you, the reality is not so simple. Actually, it's a mess. Turns out you have dependencies to worry about, you have all of these derivative data products that were developed, and then God forbid you want to change anything. We need to add a new field. We need to change the logic. Turns out we defined widgets the wrong way and we need to redefine them. You need to reprocess everything. Reality is not as simple as an architecture diagram that a vendor will provide to you. So I just want to kind of call that out. We're not selling a panacea here, right? It's very complicated. But in order to build good data hygiene or good data management in the cloud, you got to start at the bottom. Data lakes are great. They're cheap and abundant. Unfortunately, they don't have the consistency or the ACID compliance of a warehouse. What Delta Lake is the combination, the best parts of a data lake and data warehousing combined in one. It gives you the reliability and the performance of a warehouse on a data lake. And essentially, when we do this, how does Delta get there? What are the components of it? First off, we bring ACID transactions to a data lake. So every transaction that you commit to a Delta table will be ACID compliant. And how it's implemented with object store, because it's immutable, we have a thing called time travel. And essentially, if you make a mistake, you need to go back in time a little bit. As a user, you don't have to call up the DBA and figure out how to restore a database in production at the last minute because I accidentally deleted a whole table. You could just go restore a Delta table to the previous version, and that's it. We also have schema enforcement. So managing Parquet on a data lake leads to schema problems, and it's really hard for architects and administrators to kind of keep consistent schema. Built inside of Delta is advanced indexing capabilities, caching capabilities on these modern clusters in the cloud, and we've even built in auto-tuning into the API. You get fine-grained access controls on a data lake. This means traditionally data lakes allow you to secure files and blobs. Delta gives you the ability to secure rows and columns. This is completely different. This is what databases had that data lakes didn't have. And now you have that same governance strategy on Delta. The real secret sauce is how do you get this data management technique? Because Delta Lake is just an API. Delta Lake is how do I manage files on a data lake, right? But can you unify streaming and batch and have the same protocol do analytics and machine learning? That's the trick, and that's what Delta is. Essentially, it's the same core API to deal with analytics, ML, AI, and streaming all in one. Delta tables can be a streaming source and sink. They can be a batch source and sink. They're truly flexible constructs. These are how lakehouses are built. Delta is the foundation. And you can use any of the programming languages that we support on Databricks to leverage Delta tables. So if you're a SQL user in Databricks SQL, or if you're a Python user in Notebooks, or if you're a Scala user using your own IDE, submitting jobs to the cluster, Delta is the common denominator. You're all using Delta. So what is modern data warehousing on Databricks? Essentially, it's real stream processing because Spark has a real stream processing engine called structured streaming. And if you heard about Project Lightspeed at the keynotes today, it's real streaming. We're going to get down to, I think I saw 100 milliseconds latency. That's unheard of. Your warehouse could have that type of latency. How valuable would that be to your business? And we also have built-in warehouse-like capabilities. You can ingest real CDC sources from partners, or you can build your own that will ingest change data capture data from your source systems into your lakehouse. And we have partners that will help you do this if you want a UI or if you need help doing it. And then essentially what we help customers build is their same ecosystem they had on-prem, which traditionally in warehouses you called it like raw staging presentation layer. In Delta parlance or in Lakehouse parlance, we call it bronze, silver, gold. It's the same concept. It's just, we call it something else. And essentially you can leverage all of our data governance partners that can help you govern and control that data so that all of your users are working on one version of the truth. And you don't have to copy data all over the place to service your SQL analytics and warehousing use cases that will go to your BI, and then your data science and machine learning use cases that will fuel the applications of the future that your business will rely on to be disruptive. So another thing I want to talk to you about today is I've kind of set the stage for data management on Lakehouse, right? We've talked about Delta, warehousing, what that provides you. That's great. I need to serve my data up to those users, and I run a really flexible construct to do that. If you've used Databricks before, quite commonly people will say, I have to wait for a cluster to boot. This is because our technology at the time was we boot compute in customers' accounts. So that's great for you. As a customer, you can negotiate with the cloud on compute cost and use like your discounts and reserved instances. But that means you have to manage the compute. Our customers came to us and they're like, we don't want to manage this. Can you just figure out how to give me the best price performance and just give me like some knobs to tune? And so we heard that, and essentially what we've come up with is serverless Databricks SQL compute. What is this? Essentially, it's a Databricks managed compute will give you instant elastic SQL warehouse compute decoupled from storage. And it's powered by all of our latest and greatest technology to get you the best price performance on the cloud. We will automatically determine all of the complexity of managing the infrastructure on the cloud. We run a ridiculous amount of benchmarks, and we constantly are monitoring what the clouds are doing, and we behind the scenes are always kind of determining how to get you the best price performance, and you don't have to manage it. With these endpoints, they can scale up instantly and elastically to handle any type of demand that you want to throw at it. I have an experiment I'm going to be talking to you about to prove just how that works. And there's intelligent workload management system behind the scenes, making sure that big queries or long-running queries aren't starving resources from short-running queries, and it's intelligent about how it manages resources on those on those warehouse clusters. And as a customer, you get instant on. I'm talking seconds. And we're even working to reduce the time to first query. So essentially, within seconds, you can have a query being answered. And then we're also gonna allow the endpoint, the warehouses, to terminate really fast, so within a minute. So essentially, you will have only pay for what you use SQL warehouse compute on Databricks. It's currently gonna be available on public preview in AWS, and it's in private preview on Azure. If we have any Azure customers in the cloud, I'm pretty sure you would find benefits into an endpoint that will start up in a couple seconds. And you can see here by the chart, behind the scenes, Databricks SQL is looking out for your costs. As these users are coming in the morning, it's going to boot up more resources to make sure that it's handling their requests efficiently and they're not waiting. And then as they leave for lunch, it's going to give those resources back to the cloud because they're not using it. And it's making sure it's looking out for your budget. So you're not wasting idle compute on nothing. And then as those users come back from lunch and they start using the system, it scales resources back up efficiently so that they're not waiting for their queries to respond. And as you can see here, as the day goes on and progresses and finally ends, the endpoint, the warehouse cluster efficiently manages those resources behind the scenes. You don't have to do anything. It just does this for you behind the scenes. So I've told you a lot of stuff, right? Like how it works, benefits of it. But I want to now put the proof in the pudding. Unfortunately, we can't use real customer data. Unfortunately, people just won't give you their data to test stuff out and then show other people. That's really not something that exists. But what we have is these database researchers. It's this organization called TPC. Funnily enough, we were joking about this earlier. It actually stands for Transaction Processing Performance Council, but it's not TPPC, it's just TPC. But anyway, what you need to know about these are database researcher people that all their sole interest in life is to just purely objectively determining how price performant these data management systems are. And they don't really care about vendors. They just want verifiable data that they can give to the industry so they understand just what they're buying. You might have heard about TPC-DS. This benchmark is abused by every vendor, everywhere, and they will all show you a benchmark that shows you how their system is the best. And we've done the same. We broke the world record on TPC-DS. You've heard about it ad nauseum. The key thing that I want you to understand about TPC-DS is that Jim Gray, in the original paper from 1985, said, computer performance is so difficult to quantify. Really, the only metrics that you can use, the only reasonable metrics, is cost, price for performance, and throughput. And so they created TPC-DS, these 99 queries, and you can see here this chart that shows the complexity of them. That's a variable amount of complexity of queries. So they tried to sample what are all the queries that you would get in a type of warehouse so that we can judge real-world performance. So this is what TPC-DS is. So since we've already beat the world record, I don't really want to belabor the point and talk about the power run, which is what every vendor will do. Instead, we want to simulate like a real working day. So what we did is we strung up this experiment using some technology, some database stress testing technology, and we executed 10 parallel runs of those 99 queries to simulate like a bunch of users querying dashboards during the day of a warehouse. And we said, what if we repeated this twice? So it's about 2,000 queries being sent to this warehouse cluster, this endpoint warehouse. And we said we want a large serverless endpoint, and you can scale between 1 and 10. But you figure it out when you get there, like when you start getting the queries. So this is the experiment. Can Databricks SQL Warehouse handle high concurrency demands? The results are in. Essentially, what we found was that we can finish 2,000 of those queries, about 1,980 queries, in about 7 minutes. And it took about $22 to complete this benchmark. It's actually pretty impressive. To kind of give you some information behind the scenes, a serverless SQL endpoint is about 70 cents per DBU, and the large endpoint actually scaled up to just 7 clusters at its peak. So remember, I gave it 10. I said you could go up to 10. It got 2,000 queries, and it says, no, I just need 7. So what we need to understand here is it's not just scaling up to the top. It's very important to understand, because we really are looking out for your costs, right? And like Jim Gray said, the best way to determine the efficiency, the effectiveness of a system is its price performance and its throughput. So we prove here that it does fairly well. And the one thing I want to show you all, to kind of accentuate to you all today, is that not only did we process this data in record time, if you would have run this on one of the most popular cloud data warehouses in the world, it would have probably have cost you around $37. Now, we can't physically run this because we've been going back and forth with these people on the news, and we don't really want to start any more stuff with this. But what we want to be able to do is give this code to the users so you can do it yourself. Like, don't take our word for it. So we're going to talk about open sourcing this code so you can run it yourself. And finally, most people don't know Spark to deliver you sub-second query response times on small data. But Databricks SQL is not Spark. Not just Spark anymore. 33 of these queries ran in sub-second, 1 second or less. It's pretty impressive. But that's not all. Like I said, data warehousing is not just query serving. And I've had a problem with every vendor talking about TPC-DS for about 2.5 years now. Why? What about ETL? Nobody benchmarks ETL. It turns out once you actually pay and buy invest all the capital infrastructure, and you buy everything and you build out the on-prem servers, no one really benchmarks them. They're just like, well, we bought it, we're already invested, let's just go. So we actually dug up this old benchmark from the 90s called TPC-DI. TPC-DI is an ETL benchmark. It's the analysis, combination, and transformation of data from a variety of sources and formats into a unified data model. Data integration is the key to data lakehousing, application integration, and business analytics. So, what is TPC-DI? It's built off of a factitious retail brokerage firm. So essentially, they made this fake company, and they said, we want to give it some source systems. So there's a main trading system. There's an HR system. There's a CRM system. You know, they didn't have Salesforce back in the 90s, so it's like a traditional CRM system. And it's externally acquired data, so like data from a third party that they would have dropped to you. And essentially, what's going on here, some of the tasks that need to be done. There's a large historical load that needs to be processed, so a large amount of historical data that you get one shot and you have to process. Then you're given 2 incremental loads, so they're CDC-based loads that you have to process incrementally into the warehouse. And you're measured on the throughput of processing the data from the source to the target in the warehouse. So this is completely different than a query serving benchmark. This is how fast can you process data and how efficiently from a price performance perspective. And just for funsies, they include dirty data that you have to account for, bunch of business logic. There's 160 pages of business logic for this benchmark. This benchmark is unlike any other benchmark that TPC does. You're not given code. You're given a 160-page business requirements document, and you're given a data generator to produce those files, and you have to figure out the code. Because the benchmark is technology agnostic, there's ETL tools that are visual drag and drop. There is no code. Informatica, is not completely codable. Talend is not completely codable. Ab initio, these things, they're applications. You have to design it. So this benchmark was created to be agnostic to the technology. You can build it however you'd like, which is perfect for Databricks and all of the partners that we want to partner with to show you how this works. So why TPC-DI? Because they give us that data generator, we can produce scales of files from gigabytes to terabytes. It produces all types of dirty files that customers have to deal with on a daily basis. CSV, text, CDC text files, XML data. I don't know, a lot of people, I say XML, they're like, are you sure you mean XML and not JSON? A lot of the world actually still processes XML. A lot of the financial services companies still do. But this benchmark, again, is from the 90s. And then there's a data model. So all of the transformations to produce this data model are documented, and there's a lot of logic that you have to account for. It's a dimensional model. There's Scd Type 2, so you have to deal with slowly changing dimensions. You have to figure out how to code that. And it has window calculations, so that you have to calculate things over time. So lots of different things that customers have to account for. This is kind of what I want to show you today, because as I was practicing as a field engineer over the years, the one thing that customers used to tell me was, your benchmarks are great, but I get dirty data. How do you help me deal with that, with those types of real world problems? And this was actually the first benchmark I found that actually produced those types of real world problems. So how are we going to implement this? Essentially, that data generator drops these files into a location. So these are files that get dropped from a source system. It drops those wherever you want. We put them on data lake storage. And essentially, once those files get dropped, we then pick them up with a capability called autoloader. I don't know if any of you checked out the talk that Barack was giving a couple of doors down a little bit earlier about autoloader. Amazing piece of technology. Essentially, it manages file intake into Delta, super duper simple, and it's very efficient, scalable, and it's exactly one semantics, so you don't have to worry about state management and all of the complexities of a lot of the ETL that it has in it. And essentially, we auto-load the data from the files into a silver staging layer, or it's kind of like getting the data in. Then we model the data or merge the data into the gold layer, which is that dimensional model for analytics. And another just for funsies on this benchmark, it's unlike any other benchmark you've ever done before, I just want to kind of articulate that, is that after you've loaded the historical load, and you're going into the incremental load, so the CDC load, actually there's these queries that fire off to ensure your ACID compliance, because there's other queries coming in selecting data from those tables. So is it going to read dirty data? And it actually checks to make sure that you're abiding by all of the rules in the benchmark. So you have to prove your ACID compliance. You have to prove it in this benchmark. And Delta handles this elegantly. Right? We have optimistic concurrency with snapshot isolation on the reader, so there's no problem. Actually, Delta handles this perfectly. It doesn't worry about it at all. We're not worried about it at all. It's something that the benchmark has. So with that, I want to bring up Shannon Barrow, who's actually implemented this, to talk to you about it.
Thanks, Franco. I want to point out that Franco has confirmed that factitious is really a word. So it says fictitious here. We changed it, but it never made it to my deck. But factitious is a word. Thanks, Franco. Oh, going the wrong direction. OK, so we're going to level set real quick and talk about the TPC-DI. It's the benchmark so nice, we implemented it twice. The context that I'm going to provide here is just kind of describe what it is that we built and where we are with the TPC. So the results and the data that we're going to talk about today, it is unofficial for the moment. We are working with TPC about how the benchmark is actually processed, some of the rules. We've also had some data quality issues with the data generator that we're working out with them. But we're working with TPC, and thanks Tillman if you're watching for assisting with us on this. So instead of actually going through probably dozens of notebooks live, which I was completely open to doing, I don't think we have 8+ hours to do that. So we're gonna talk about what is given versus what we created just with a single example, okay? There is a customer dimension table that comes in, for example. And when we talk about what they actually provide, the data looks, or the documentation looks a lot like this. And I know it's a lot of words on this slide, but the left is actually the documentation, and on the right is just a little bit of a summary, okay? The historical is coming in an XML file, all right? It's read, you actually read only a subset of that XML file since it's actually shared with another table. Each XML record is actually only a single column of the data set or that customer's record, and you have to coalesce it with all the previous records, okay? So it's similar to that kind of, if you've ever worked with Golden Gate, similar to that kind of concept, but it will actually bring in the record, tell you the update that's happened, and you actually have to actually push the record's new value to the old record. It also has history tracking, so we have to handle it with an Scd Type 2 approach. Every customer record is actually going to have an effective date and an end date. So you actually have a surrogate key that you can use with other records. The problem is that the incremental data is actually read from a TXT file with a completely different schema. So the different schema will come in, you have to read it, then you actually have to put that data in each of the additional incremental batches. There's complexities with surrogate keys that you also have to handle downstream so that you make sure that all the other tables that reference that record from the DIM customer table has the correct customer surrogate key now. So just to give you a quick example of how we had to go about implementing some of that, on the left you'll see an example of how we went about maybe handling the phone numbers, since there's a little bit of complex logic you see there on the left, as well as how we had to do a window for every single record for the historical data and coalesce it to account for the null values that we don't have on certain previous records. In the end, there's probably about 99 other pages of documentation that we have to handle like this. It was definitely a joy. Thanks, TPC. So how did we make all this possible? Why are we actually now able to outperform, in my opinion, some of the data warehouses that this was originally built for, okay? So Delta Lake does become the foundation that helps make this possible. The fact that you can automatically generate identity columns now for surrogate keys means that you can create it and it's all managed under the hood for you. Additionally, we've made some performance improvements to how the merges happen, including Scd Type 2 and Scd Type 0, so every merge that needs to come in to update existing records will now be handled under the hood in a much more performant manner. And at the bottom here, I list an example of how we did it for DIM customer for a surrogate key. So as you can see, there's a surrogate key for a customer ID, and it's generated always as an identity column. And when you load the data into the table, you don't include this column. Delta handles it for you. What are some of the additional knobs that Delta provides? The generated columns that aren't identity columns were actually leveraged in this case for partitions to help us index the data a little better. We did not leverage Z-order, for example, because it's more of a consumption layer advantage. So if you Z-order the data, you can actually consume it in a much more performant manner. But since we don't have that consumption layer, it's not used for the benchmark. This actually gave us a way to additionally index the data. Where it really became more effective was the merges that need to happen. So we could actually take data that's been either updated or completed. Maybe the data is now actually stale, it's for a previous iteration, or it's completed now. We can actually move that over into a different partition. Additionally, we were able to leverage some of the Delta underneath properties like tune the file sizes for rewrites, make sure that you're actually writing files that are a little bit smaller because there's going to be a lot of merges on this table. And here's an example of how we were able to leverage the generated column for the fact watches table, for example. So the fact watches table has a date removed column, and once it's removed, you never actually need to update that table. So if we're able to partition on it, we now can move that to a directory in storage that can now never actually need to be consumed again when you're doing merges. So let's talk about orchestration. How do we automate this orchestration? So this is actually one of the cooler pieces we'll show here in a moment, is that we leverage workflows to do this. And actually, I think this time last year, there was a feature within workflows that wasn't available that is today, and that's the fact that we can now leverage cluster reuse. So use a single automated cluster, have every task within that workflow, this multitask job, now reuse that cluster as it continues through the pipeline. Repos were a huge advantage, having that Git integration so that the teams that we have spread across the country can all work on that, as well as be able to actually use arbitrary files, so JSON files and YAML files that have different properties. So we were able to automate that as we're working through the entire pipeline. And then we actually all packaged this up using Jinja. I'm not sure if anyone's ever used it before, but it is a templating engine that allows us to consume the JSON file with all the job properties that are either declared as dependencies for each of the different notebooks, or you can pass in dynamically. If I can find my mouse. There we go. Let's see if this works. And no, so let me do. Let me go back out of full screen. Just exit slideshow. Okay, does it show up now for the video?
Yeah.
Good, okay. So let's talk about how we were able to do the benchmark. This is actually our driver. Now this particular driver is the only thing. We are going to make this data or the code public once we finish the benchmark, by the way. So the idea here is that anyone who wants to be able to pull this code down from Git, you can pull it down, use this driver, and it will actually launch your multitask job, your workflow for you. No hand coding on what you need to do. So this driver itself, if you were to run this, would actually create the entire multitask job for us. So actually, let's go ahead and start this up now.
Risky click.
Franco actually set up a line of code in this notebook that actually completely exits from the notebook just to make sure you don't get to the bottom without running the steps above. But what we've done is we've actually configured all of the properties at the top here for being able to launch this. All right, so now that's finished. There's a data generation step in here, but since we already have the data, we're going to skip past this one, and we're gonna run all below. There's only one extra little line of code here, or one extra cell. So once this actually finishes, we're gonna get a link here to be able to open up our actual workflow. I think my internet's just not working today, huh? There we go. Okay, now we have a job. Got to warn you, it's a rather large job. Wow. So by running that single driver, the entire workflow is scripted. Now I know this looks very small. Don't worry, I'm going to zoom in. But to give you context of how many steps are involved in getting the TPC-DI done, this is it. So as we mentioned earlier, there's a historical aspect to it, and there are incremental updates. And in between the historical and the incremental, there's audit checks, okay? So as you're going through, you'll see everything in the historical finish up. We go through an audit check, and then we'll actually end up going through update 1, which is batch 1, and then update 2. All right, let's go ahead and kick this off. All right, while that's running, I am going to show you our Jinja template, just so you have context of what we built. So this is how we were able to script the orchestration, okay? As you can see, just a simple JSON. Dependencies are set, libraries are set, notebooks are set from what the location. But as you can see, none of the actual notebook locations are exact. It's just pulling from a Git repo, okay? So if you were a different user being able to launch this, it will automatically pull the version you've pulled down. All right? and here's our run going. Okay. While we are waiting for that to run, wanted to show a couple things here. What's important to me is, I can show results here in a moment that show you, hey, how fast certain runs ran. We've got different scale factors. We ran everything from 10 to 10,000, okay? 10,000 is a terabyte worth of raw data. I think there's 16 billion rows, okay? But in the end, a lot of that really doesn't make much sense until you start looking at, how does it compare to different other variables that might be involved? Photon, what series was the best? We were using AWS to run these benchmarks, and when I tried running them, I would converge upon maybe what the best number of cores would be, and then I'd run that on various different, variables. We'd have Photon, we'd have not Photon. We'd run it on M series, we'd run it on, the R series. We'd run it with everything from 96 down to 16 core nodes, okay, but always with the same number of cores within the cluster. And so what this slide is trying to show, or what this visualization is showing, is what is the performance compared to a baseline, okay? So when we talk about how does Photon perform, it does outperform. It runs much faster than the non-Photon versions. The one key thing about Photon here is it would actually run even much faster, but this is not an optimized Photon workload. An optimized Photon workload wouldn't be reading from XML. It wouldn't be reading from a CSV or a text file, okay? It would be reading a Parquet file, for example. It also has the longest running stage in here is actually on the biggest data set. It's a window that does a range over the last year. And that's something that today is not photonizable, but is being worked on, and so will be photonizable soon. So once that's done, then it would actually significantly outperform. The benchmark itself, though, really does focus on total cost. So I'm going to summarize maybe where, let me go back into the slideshow. Where we end up on as far as the total cost per billion rows. Okay, so the way the results work for the TPC-DI is it's a rather elaborate algorithm they use. In our case, what we're actually doing is really just simplifying it here. It does boil down to how much does it cost to process the rows, okay? So simplified TCO approach here is based on the cost per row process. So these were the best performing combinations with on-demand pricing. So our entire runtime went from 24 minutes on the fastest with Photon versus 36 minutes, okay? So this is actually 16 billion rows. It's a terabyte worth of data through the entire pipeline I showed you. So we're not just pulling it in and putting it into a table and calling it a day, okay? We have 3 batches. We've got surrogate keys that have to be passed through. We've got entire joins. We probably have in the neighborhood of 100 to 150 windows that have to be done within this pipeline. So we take that, we look at how the speed to performance works, and if you look at the price per billion rows, even though this is not a Photon optimized data set or job on the ingestion side, it still is roughly equivalent in the price per billion rows. But the non-Photon version runs 50% slower. I did actually run this on spot instances as well. Actually, all of our tests were run on spot instances. The price above it, that you see here in the chart is actually the on-demand price. But when you run it on spot, it's actually even cheaper. So 85 cents was the best result for a billion rows. So what did we learn? You probably saw some from the chart here a moment ago, but Photon is consistently faster. TCO is approximately the same. It's generally about 4.5% more expensive, but you do get your results about 50% faster in a lot of cases. Graviton, I'm not sure how many how many AWS customers we have. I know the ARM-based series is not available on all clouds, but the Graviton instances were significantly faster and cheaper, okay? So 40% less TCO than x86. Cluster sizing, core counts being equal, this was actually a surprise to me. The smaller nodes that were more plentiful actually ended up having the better performance, okay? So all the way from 96 down to 16, same number of cores being equal, opt for the smaller nodes. If anybody has any theories why, hit me up after. Also high scale factor. So if you look at the high scale factor, what's the optimal worker optimization? So in this case, the general purpose ones were better than the memory optimized ones. It's probably because the fact that we have very few big files. We have a whole lot of 128 megabyte files, which actually does not force us to need a memory optimized one. So we do have some obstacles here. First of all, I can tell you it took a lot of effort to fix the audit issues. It could be because maybe I'm a bad coder, or there's a lot of complexity in their documentation. One way or the other, it did take me a long time to kind of work through all the audit issues, but in some cases, we had to look at how they got, or the actual end expectation for results, and kind of back into it by interpreting it that way. Orchestration complexity. So when I showed that we could launch this from the driver, there is a lot of complexity in the JSON that needs to be updated. That JSON, I think, is approaching 2,000 lines of properties at this point. And so there is some maintenance you would have to keep on making sure that job is up to date, right? So there is that's a long-term decision to make, is whether or not you can actually keep that updated and consistent across your environments. And data quality. This ended up being the bane of my existence here about 2 weeks ago. So we actually spent an entire weekend, I think, trying to identify where my audit issues were coming from. And I probably still had a dozen or more audit issues coming through on some of the higher skill factors. And eventually, after hours and hours of working on it, I finally identified that it wasn't a code issue. It was that the data generator was producing some results that did not actually match up to what the audit records were showing. So, and for an example, I think there were missing stock symbols from the dimension table that never even came in the files, but were showing up that were actually being sold, for example. But in the end, that took a lot of time to kind of work through those things. And so a couple of these we're actually going to get into here in a moment as Dillon comes up and talks to you about DLT and how we could have actually made our lives a lot simpler. So thank you. Dillon, come on up.
All right. Hey guys, I'm Dillon Bostwick. I'm a solutions architect here at Databricks. I've spent a little over 4 years at Databricks helping our customers build out their architectures. And more recently, I've helped build out a team of product ambassadors who focus specifically on Delta Live tables. So now I'm going to be walking you through how we were able to use Delta Live tables to make TPC-DI so fresh and so clean. Okay, in other words, how do we actually build out a real-time data warehouse? So data freshness and data cleanliness, these are common terms that as data engineers we like to use to describe the properties of the output of our ETL pipelines. Okay, we might care more about accuracy, we might care more about latency, and what are the kind of sacrifices we have to make, right? So fresh and so clean, for those of you who don't know, is also the name of an Outkast song that came out in the early 2000s, okay? And not unlike many traditional on-premise enterprise data warehouses, Outkast really had their up and coming in the early 90s, right? And they really peaked in the early 2000s, right? However, perhaps unlike some of these traditional data warehouses, one of the things that Outkast did really well, as you can see here in this image, was they were obviously fresh and clean, right? You can't really deny that. But what they did really well as a hip-hop group is they kind of pulled off this style in this really elegant and simple way where it didn't look like they had to spend millions and millions of dollars to be so fresh and so clean, okay? So, why do we care about this? Why do we call the talk so fresh and so clean? Because really, as data engineers, if you zoom out at the big picture level, when we're taking different kinds of technologies that are optimized in different ways and we're stitching them together into a data architecture, what we're really doing is we're trying to figure out what is the right kind of trade-off we want to make in the SLAs and guarantees we're actually giving to the consumers. Okay, so when I'm helping our customers think about their data architecture, what I'm really doing in my mind is thinking, what are these kinds of trade-offs? These are a couple of dimensions. Obviously, there's a lot of other things we have to worry about. But oftentimes we're trying to decide, do we want to prioritize latency, right? What are the implications of data cleanliness? You think about data cleanliness, I can have the most robust, high-performance architecture, but if people at the end of that architecture don't trust the data to make decisions or train machine learning models off of it, it's essentially useless, right? And even worse than not trusting data could be mistrusting bad data. So this is the kind of high-profile situation you see in the news nowadays, inaccurate machine learning models costing companies millions of dollars, costing them a lot of reputation. Oftentimes those models are trained on inaccurate data, right? Slightly kind of less visible, more of a hidden cost is the idea around operational efficiency. And I oftentimes run into this when I'm not working with customers. Sometimes I'm also helping build out our internal reporting. And what I find is I spend more time in Slack than I do in my query editor, right? Because writing SQL queries on cleaned up gold data is pretty easy. But the hard part is when you have 3 different tables and they're all called latest CRM gold aggregate, but they all say different things. And so what I'm doing is I'm going into Slack or I'm sending around emails like, who was the last person who queried this? And what's the actual source of truth on what transformations were happening, right? So that's that idea of lineage, which we're gonna talk about more in a little bit. And obviously, as data engineers underlying everything, we can always throw more compute at a problem, we can always throw more engineering time at a problem, but usually there's a budget we have to work within. And at least for the purposes of this talk, I would say cost effectiveness is highly correlated with the overall simplicity of the architecture. Okay, so what I'm gonna do now is I'm gonna walk through a couple of different common design patterns to really solidify this idea that we have to make trade-offs, and then use that as a context for what we're really trying to do, which is create this idea of a real-time data warehouse and use TPC-DI as a case study, because we think TPC-DI, like Shannon and Franco have shown, is really representative of this idea of the kind of more traditional on-premise warehouse. Okay, so first we have here this enterprise data warehouse, right? And this is the kind of traditional idea, but ETL pipeline. And the concept of data freshness really come from this idea where, in the data warehousing world, sometimes you have to compete for resources, right? Because you're working within a fixed capacity appliance. You don't want to compete for compute during the day with the ad hoc analysts, so you're usually running batch ETL at night. Okay, so let's say, for example, we're running a nightly batch ETL pipeline. It takes maybe 12, maybe 24 hours for it to complete. What that means is when I go into my decision support system or my BI tool on a Monday morning, I'm actually looking at the state of the business as of last week. I have absolutely no way to know the current state of the business when I'm running these nightly batch ETL pipelines, right? So data freshness in the batch world is really a function of frequency of refreshing the batch as well as how long it takes, otherwise known as like the worst case end-to-end latency, okay? So one of the things that data warehouses did really well, and this is an example here, is this relational diagram from TPC-DI. So we follow our Kimball, we follow our Inman best practices, we have all these features like referential integrity, right, or compensating transactions. We all have, we have these common data models, and these are all features that really make sure that at any point in time when I go to query the table, I have a really high integrity, consistent, accurate view of all of the different business objects. Okay. That being said, we lose data freshness, and usually you have a really high upfront licensing cost you have to pay. I would actually argue that cloud data warehouses are a step in the right direction towards simplicity and cost effectiveness. Like Franco mentioned, one of the things these do really well is they separate compute from storage, so you're only paying for what you use, and usually the maintenance is a lot easier in the cloud. Okay. But that being said, I would actually also argue that cloud data warehouses don't necessarily solve for a lot of the challenges that we ran into in the traditional on-premise warehouse world. Notably, they don't have any native support for real time. Okay, so if I do want to start improving the freshness of the data I'm working with, I have to bring in my real-time frameworks. And in the cloud data warehouse, it's still proprietary. I still pay for egress. So then I have to think about what does the data movement look like when I want to start bringing in my real-time frameworks. Okay, a little bit outside the context of ETL is also the idea that the serving layer in these data warehouses are still built for really high concurrency BI. We talk a lot about, at some of the other talks in this conference, about the idea that, think about modern analytical needs. Training machine learning algorithms or doing hyperparameter tuning, those require query patterns that are vastly different. So even thinking about how we do the caching is really different, okay? Swinging the pendulum, right, we have our big data tools that take advantage of commodity hardware, and we have our real-time frameworks. So think Apache NiFi, Apache Flink, Kafka ecosystem, obviously Spark structured streaming as well. And all of these frameworks, they give you unbounded processing. So I can do incremental updates, usually at the second, maybe sub-second latency. So I know people who do real-time, they like to argue a lot about what's the difference between near real-time and true real-time. Okay, but if we take semantics aside for a second, think about really true use cases where milliseconds matter. So think maybe like high-frequency trading that a lot of hedge funds do, or maybe like real-time bidding, which is a use case in the ad tech space. These are use cases where sometimes even a microsecond is the difference between you being able to make a trade or being able to bid on an ad and you're actually being profitable, right? But I usually have to spend more compute, I have to spend a lot more time to kind of shave those milliseconds off. So I think that's a really elegant example of the sliding scale between profit and cost, or otherwise, latency and cost. Okay, but those aside, if we just kind of look at real-time warehousing, usually milliseconds don't matter. When I'm a human and I'm looking at a BI report trying to make a decision, like a business decision, usually seconds or minutes are really what we care about. And if we can do better than nightly or weekly, then usually we're seeing some improvement, okay? Say, for example, you're a data provider, where your entire business is you curate data and you sell them to external consumers. Sometimes you have an SLA in your contract where you can be penalized if you're not able to update data by like the end of the day, okay? So we have a lot of customers that always come to us, and I deal with this a lot in the enterprise space, where they come and they say, we see huge competitive advantage if we're able to do the whole real-time warehousing idea. And we go, that's great. We can do structured streaming. We can give that to you. But then we actually look at what they have today, and they usually have some sort of implementation of batch that's representative of how we used to do data warehouses, back in the 90s or, back in the on-premise days. And what we realize is there's a huge barrier to entry to make it into the real-time club because the mindset change is so huge, right? So skill sets need to be different. The really paradigms themselves are different. So what do I mean by paradigm? To give one example, like say for example you have an outer join, right? In the batch world, we all know how to do outer joins. It's like, pretty easy to reason about. If you do an outer join in a stream, do you do a stream outer join? Because if you do that, you have to think about this thing called watermarking, and that's a whole different concept. You actually have to deal with multiple watermarks. So I would actually argue refactor that, and then maybe do a series of cascading merges instead, right? So you're really rethinking how you're actually reasoning about the data itself. The other thing is when you're going from batch ETL and you're refactoring it into streaming, sometimes you end up with dozens and dozens of different streams. So then you have to figure out, okay, I'm gonna put that into production. How do I actually run those across a number of clusters so that I'm provisioning at the right capacity for the sporadic nature of real-time jobs? And so I have to do all this extra thought, especially in the cloud because you're paying for it 24/7, and it's kind of difficult to do auto-scaling with streaming. And so I would actually say low latency streaming, that's where it is in my trilemma because you lose a lot of that simplicity. The other example I want to give before we move on, then we're going to talk a little bit more about TPC-DI again. If anyone has spent a lot of time doing Spark structured streaming, you probably recognize this image here. This is the idea of a watermark, and it's all over the streaming documentation. So this is actually how a lot of us learned how watermarks work. We could probably do a whole deep dive session for an hour and a half where we could just get into the weeds about watermarking, and we're definitely not going to do that right now. But the idea behind a watermark is I could have a really short watermark, but the problem with that is I lose late arriving data. So my late arriving data won't make it into my aggregate or my join or my window. Alternatively, I can have a long watermark, and I'll be better at providing high accurate data because I'll be more compensating for that late arriving data, but then I inject latency into my pipeline because my microbatches won't progress further. So to put it simply, watermarking is also a really elegant example of that sliding scale that we have to choose between being clean or being fresh, right? Being lower latency or higher accuracy. So it's really hard to be so fresh and so clean, okay? I'm gonna give one more example before we move on because I know some people are looking at this and saying, we figured out how to do this already. You don't need to introduce all these new tools and do this whole real-time warehousing thing. We figured it out. All you do is you take your real-time framework, you process everything throughout the day, and then in parallel, you reprocess everything with your batch framework, and you put all your more advanced quality checks and transformations in your batch framework, right? So this is an idea of what we call Lambda architecture, and I'm not saying there's anything inherently wrong with the Lambda architecture. Matter of fact, a lot of these are running in production today, a lot of them quite successfully. We figured out how to do this with Storm, so people would usually use Storm, then they would reprocess everything with Hadoop MapReduce. But the challenge with a Lambda architecture is what we're basically doing is say, hey, I don't want to make the sacrifice. I don't want to have to choose between being fresh and clean, so what I'm going to do is I'm going to throw a whole bunch of different tools and over-engineer the problem. And this is kind of a typical thing that we ended up seeing with Hadoop, is we had to throw a lot of different tools at a problem to solve it. The other thing we lose is we don't have a single source of truth. So people go to the serving layer and they don't know, do I query the speed layer? Do I query the batch layer? It's that same problem, what's the actual accuracy, okay? So now we have this idea, we already talked a lot about this Lakehouse idea at this conference, and what Delta Lake does really well is it allows you to do concurrent batch and stream reads and writes on the same table. All the while, I can have isolated queries for my feature engineering, my machine learning algorithms, and my BI reports, and I don't have to duplicate any of the data, right? The fact that we can do those queries, that's isolation, right? So that's the I in ACID, right? And the fact that we can do concurrent streams in batch, right? That's the C, the consistency in ACID. Okay, so what Delta Lake does is it says, we'll take care of the systems level guarantees so that as the data engineer, I'm focusing a little bit higher up the stack on the business logic. And then if we move up the stack, we look at Spark. Spark is a general purpose compute engine. What it means is that I can have the same API for batch and streaming. So I write all my data frame, I write all my SQL code. When I'm ready to start using streaming, I don't have to go learn a different interface. I'm still writing Spark structured streaming on my data frames. Okay. So I know we talk a lot about the benefits of Lakehouse. Like I said earlier, usually the problem isn't necessarily like seeing that vision. Usually it's about how do we actually go from the batch world, because there's a lot of things that were really great about data warehouses. We're not necessarily saying we have to rethink everything, but how do we keep those things that worked really well in the data warehousing world, give you the freshness and simplicity, give you those real-time benefits. And really what we want to do is, I know so far I've been a little bit theoretical in my ideas here, we actually wanted to use TPC-DI as that representation of a data warehouse and then make it to work in real time. So how did we actually do that? The way we did it is we used a feature of the Databricks platform called Delta Live Tables. So Delta Live Tables is essentially an ETL framework. It just went generally available last April. And the core premise behind Delta Live Tables is it says, if you can be declarative about the data flow, you can still write your code in either SQL or Python, but if you're declarative about the data flow itself in your overall ETL pipeline, that gives the Delta Live Tables engine so much more visibility about what you're trying to do, and that affords us a lot of benefits. So we can now automate the infrastructure for you, okay? We can now automate orchestration for you. We can give you lineage. We can basically handle all the monitoring for you, and then you can be declarative about how you want your data quality to look, and then we'll also run those constraints on data quality for you, and we'll be declarative about the whole thing. And those are all the benefits you get simply by defining your data flow a little bit differently than how you might have done it in the procedural world. Okay. So you might be wondering, Dillon, isn't SQL already a declarative language? And that's absolutely true. SQL is a declarative query language. But what DLT is saying is let's be declarative about the flows, as in the transformations and relationships between the tables and views themselves. So every data set in DLT is either a streaming data set or a batch data set. Data sets can be tables or views, the exact same as it would be in non-DLT Spark. I call it non-DLT Spark. I don't think the name dead tables is really going to take off. So, when we're not in DLT, things are either a streaming or batch. And if I want to go from batch to streaming and say I'm just writing simple SQL, I don't have to do anything different other than change that keyword and then put the word streaming when I define my table. I don't have to think about checkpoints, and I don't have to write the typical scripting or boilerplate code that I would typically put into my Python or my Scala when I used to have to do this without DLT. Okay, so here's an example. Here's some mock code I have on the left. I have my streaming table. That cloud files, that's going to use autoloader, which Franco described earlier. So I have my flat files. We use this for CSV, and this is how we actually did it when we took TPC-DI and actually ran it on DLT. And then we create another streaming table, that's our bronze table. We put a little bit of metadata in it, and we can actually sync that with the Unity catalog. And then one of the things that you might want to do as a design pattern with DLT is as we start getting downstream, you actually might not want to use streaming. So as we start talking about the gold layer, or the silver layer sometimes as well, you actually might want to keep some of your tables batch. So DLT gives you that ability to toggle without having to change a lot of your mindset. And the reason you might do that is some aggregates are really, really difficult or expensive to recompute incrementally. Some aggregates are actually impossible to compute incrementally. So in the real-time warehouse, there still is going to be a need for batch, but you as the developer get the ability to choose when you want to introduce batch, and then DLT is going to handle all of the scheduling and orchestration around it for you. All right, so this is this idea of automated orchestration. So what DLT, I like to think of it as it's kind of like compiling your ETL pipeline. So if we were to write this procedurally, and we would say do this, then do this, then do this, right? That's that procedural or imperative logic. Then we would bring in an orchestration tool like Airflow or Azure Data Factory, or maybe we would actually use Databricks multitask jobs. And there's nothing inherently wrong with these orchestrators. We actually want you to use those kinds of black box orchestrators alongside DLT. Right, but with those procedural kind of logic, there's a lot more kind of manual effort you have to do. So with DLT, basically automatically generate and infer the DAG. So we're able to kind of generate, we basically give you lineage. And through that DAG, we automatically figure out how to schedule both your streams and batch. And you can do that in either triggered or continuous mode, okay? When we took TPC-DI and we wrote it in Spark SQL like Franco showed, and then we took it and we rewrote it into Delta Live tables, we were able to reduce the end-to-end latency of the pipeline by about 50%, so basically twice as fast. And a big part of the reason we could do that is because when we ran DLT and DLT orchestrated it automatically, it was actually smarter about the decisions we have to make about how do we parallelize and run things the optimal way. So it was actually able to utilize the cluster a lot more effectively. And what you can see here, we're running it with 72 different nodes. And if you look at the server load distribution, this is just a screenshot of Ganglia, we're basically perfectly using the cluster. Like, you can't really get better than that. The green is just the driver, but everything else is being pretty much well utilized. And that's because DLT was better at figuring out how to orchestrate the pipeline than when we tried to do it manually using Jinja templating. The other thing is there's a lot less overhead. So with TPC-DI, you have this idea where you have to audit between individual tasks, whereas with DLT, it's basically running all those tasks in parallel and it's figuring out how to do it in the most continuous fashion. Okay, so just the automated orchestration alone had a huge impact on latency. The next thing I know I mentioned earlier around DLT is we have this idea of automated infrastructure management. Okay, one of the really biggest things that I think DLT gives you, even if we don't even talk about lineage and all the other stuff, is that we can now auto-scale streams. The way you used to have to do this was if you had maybe 50 different streams running in production, maybe you wanted to have 10 streams running against 5 different clusters, for example, you'd have to figure out how do I actually provision it in a way that handles that peak load. So when we took, we actually stood this up with a pretty large tech company here in the Bay Area, which we actually mentioned earlier in the keynote. We reduced their compute cost by about 40% compared to the previous month, and that's simply by turning on auto-scaling, because previously they had to over-provision their clusters to be able to handle the load that you have to deal with streaming. Okay, so with Delta Live tables, we have this idea of backlog-aware scaling, or we can actually talk to the streaming source. We can talk to autoloader. We have a lot more visibility into how the microbatch is coming down the pike. Okay. The other thing I mentioned is we can be a lot more prescriptive about data quality. Right, so we have this indisputable understanding of the constraints we want to apply to our data. And this was actually hugely useful for Shannon when Shannon was coding TPC-DI, because we actually ran into some issues with the data generator that TPC had provided us, and it would have been a lot easier if we actually used these quality constraints to detect it. Okay, so how does these constraints look? So what you can see here is we implement this expectation syntax. And one of the things we do a little bit differently than constraints in other databases is we give you the ability to take an action upon violation of the constraint. So in this case, you can see we have on violation drop row. Okay, that's just going to get rid of the row. One of the use cases we can use with this is you can make quarantines, right? So if you want to have a separate table and then you can kind of like negate this expectation, the filter I have, on violation, send it to the quarantine, and then we can do manual remediation on the bad data, because maybe we don't actually know what's wrong. Maybe that could be indicative or a symptom of other problems with our data. You can also drop the entire batch on violation. Maybe you're buying data from an external vendor, and you want to, maybe you want to throw out the whole batch if there's an issue with it. Okay. The other thing I can do is I actually don't have to specify a violation at all. And so why would I do that? The reason I would do that is because at runtime, DLT is automatically logging everything that happens, every event across the entire pipeline, and it actually puts it into a log table. And guess what? That log table is actually a Delta table. What that means is we can then build real-time reports. So we can actually have a real-time view and monitor all of the different data quality constraints as they're happening in real time. So to give an example in terms of TPC-DI, this is some of the code that we wrote for TPC-DI. And you can see this is the constraint that we added. A little bit further down the query, you can see these left joins. Now, typically, if you were implementing TPC-DI without this, you put an inner join. We're saying put a left join, but then we're going to apply a couple null checks on that left side of the table. And what the DLT GUI gives you is, you can't really see it, but down here at the bottom, there's this expectation, we called it valid symbol, basically making sure that the symbol's not null. And less than 1% of the time, that null check was failing. But that being said, there were still over 1 million records where basically that customer ID was null. But it would have been really, really difficult if it's less than 1% of the time where you're having bad data. It would have been almost impossible to figure that out. And I think, Shannon, you spent like an entire weekend trying to get to the bottom. Yeah, don't get me started. but had we put the constraints in the beginning, we did it without DLT, then we redid it with DLT. But if we started with DLT, we would have actually been able to automatically detect that before it happened. It would have been a lot easier. And then I also want to show you, it's the first tab. All right, so when I mentioned earlier, 10 minutes, okay. Wrap up in a second. This is a Redash dashboard we built on top of those Delta logs. So one of the things you can do is you can build dashboards around your quality KPIs. Your quality KPIs might say, I want a certain amount to pass in bronze, then silver, and then maybe gold has to be 100% compliant with my data quality constraints. This is actually how we did it for TPC-DI. And what you can see at the bottom is, we have one of these constraints that's failing a lot, and that gives us a whole different visibility. And then also our data analysts can log into this dashboard. They can actually make sure, okay, the data that I'm looking at is high quality. These are specifically the constraints, and I can actually train my models off of it. All right, one last example, then I hand it back off to Shannon because I know we're almost out of time here. One of the other use cases that came up with TPC-DI is change data capture. And this is obviously something in the traditional warehouse world is super important to be able to do. I just want to clarify, because some people get confused on this, we are not replacing the Golden Gates or the Debeziums or even the Delta CDFs of the world. Okay, what we're doing is we're integrating when you already have that change data either coming from a CDC tool, or in the case of TPC-DI, TPC-DI's data generator actually gives you change data. So what DLT implements is basically a wrapper on top of the merge and do capabilities of Delta, and it makes it a lot easier when I want to do CDC. The way I used to have to do this is I would have to write like 200-line merge statements where I would manually have to take into account deletes. I would have to figure out how to manage my keys. But what this does is it gives you basically a single command. I give it my key. I can specify a delete condition with a single line of code, and then I can sequence by either timestamp or version. So depending on how you're getting that change data, it really doesn't matter what the CDC source is coming from. You can basically hook DLT up to it, and we'll natively process that change data, put it directly into your bronze or silver table. And again, you're not having to write a lot of this boilerplate for each batch, kind of difficult to reason about streaming code. One last thing was Scd Type 2. I know we're out of time, but Scd Type 2 is another thing. This is in preview, and it's just another example of taking warehouse-style features and implementing them natively without having to do a lot of extra work. So if I add this extra line of code, it'll automatically make my data look like this, and I don't have to go in and think about what are my best practices. If you're doing Scd Type 2, which is obviously a really common use case in the warehouse, I want to start doing it on Lakehouse. I add that line of code. This is just like another example of how we make it easier. Cool.
Thank you. Really regretting not mirroring instead of extending. Okay, just speed run here. Let's take a look at here we go. So this is earlier we showed you the workflow, okay? And in fact, we launched that workflow, didn't we? So let's actually take a look and see, did it finish? There we go. That was our workflow completed now, okay? So for reference, let's take a look, zoom out. This was our workflow. Now, by comparison, this is our live table. Not quite sure who made the decision to make one vertical, the other horizontal, but at least you can know the difference. One's vertical, one's horizontal. Okay, so as an example, let's take a look. The one major table we had the issue with on the data quality, for example, was fact watches, okay? So let's find fact watches here, and I can show you where we had the issues. And if you scroll down here, you can see where we're still getting the data quality issues, okay? And let me try to zoom in. Okay, so if we wanted to take a look at it's actually none of the customer IDs were failing, okay, but less than 0.1%, which does indicate how many rows we're actually processing here, were the ones failing, okay? And so luckily we're able to build the metrics that Dillon showed earlier to show actually all of the different tables in one snapshot, how many are failing or do we have an issue, okay? Like I said, speed run, I would have gone into more detail here, but please hit me up after the fact and I am more than happy to show a lot more. I'm going to give a couple of caveats before I talk about the benchmark. Now, DLT is excellent. It's still in a position what I considered DB-SQL was last year, right? It's going in the right direction. It's a really cool tool. We need to clean up a couple of things, and it's about to be amazing, okay? Talking about how we compare it, right, to the traditional notebooks, a couple of caveats here. It was not developed to be submitted for the benchmark, so we did not do an audit test between the batches. The way Delta Live Tables works is sometimes I think of it as like the next generation of processing. You just tell it to go pick up your data, and it processes it all the way through. So it's not always so easy to stop it between a batch, say, all right, I need to count rows, and then now you could go to the rest of the data, right? So it's a little bit difficult to do that. And we were never intending it to be pushed into the benchmark. It's primarily used to show you how you would use something like this in production, okay? The other piece of this is that it doesn't use Scala at all. So today, you cannot actually add the XML library that we're using for the customer management file. So if you were to run this yourself, we actually have the driver. If you choose DLT, it will create a two-step workflow. One is to build the customer management or ingest the customer management.xml. The second step would be to launch the rest of the job. But now, that takes about 3 minutes. So any timings you see here, just add about 3 minutes to it to get an equivalent to the traditional side. So in the end, it takes, at best, 24 minutes to process it on the traditional side. It took 10.7 minutes to process it in Delta Live Tables. In the end, we actually got a result that was $1.01 for Photon, 93 cents for non-Photon, and again, same result. Runs about 50% slower in non-Photon, but slightly better on the price of performance, okay? And that's what the benchmark uses. And then if you look down at the bottom, the spot instance actually dropped just all the way down to a 58-cent price point. All right, Franco, you want to wrap us up?
Thanks, everybody. So to wrap up, what we've showed you today is data warehousing essentially consists of ETL, storage, and query serving. Why would you pay 3x or more for just warehousing when you can build a data platform that has ETL orchestration and data quality with Delta Live Tables, machine learning and AI built in with AutoML, and SQL warehouse serving all on one copy of your data in Delta Lake? I don't know why you'd want to, but there's just one more thing I want to tell you. We saw a lot of code today. You could do all of this with partners and not write as much code. One of them is here with us today, some of my favorite people. I come from a visual ETL background. I prefer tools where I can visual drag and drop. I know I'm at Databricks, right? How the heck could I operate here? But I have some really good friends over at Prophecy. And there is no coding required or low coding required with Prophecy. You could design this entire ETL benchmark and not have to write all of the complex code that we designed today. And actually, we're working with Prophecy so that you can actually use this as an example workflow to how you would design this. And they're here with us today, so if you want to talk to them about their low-code data engineering solution, please check them out. They're in the Expo Hall, and Scott, one of my favorite engineers who's been helping us write this thing on that tool to do that. So no coding required to actually do this stuff. If you know anything about Databricks, it's kind of unheard of. So I just want to make sure you all understand that it doesn't have to be complicated. It doesn't have to be complex. We've actually got some really awesome partners that help with this. I also want to send out a shout out. This was a tremendous journey. I had the crazy idea to do TPC-DI about 2.5 years ago, and everyone, actually, first off, they laughed at me. You can't do that on Databricks. I said, hold my beer. There were a lot of people that came together at Databricks to make this thing happen. So I want to call out to Alex, Brad, David, Itai, Joe Harris, and Joe Russell, Lauren, Max, and Nico. We could not have done it without a team of people to actually make this happen, and it's been an amazing journey. With that, we're going to open up to questions. I'm going to bring Shannon and Dillon back up here. If you have questions about anything that we talked about, we have one of our colleagues is going to bring a mic around to make sure that the people that are watching can hear your question, and then we'll go ahead and answer your question.
We only have like 3 minutes, so maybe just one awesome question. If anybody's got a super juicy one. Yeah, I see a hand. I'll bring the mic.
So how can we handle the late arriving in the delta concept, delta tables?
Late arriving data?
You want to talk about that one?
So the question was, how do we handle late arriving data? So if you're talking about a stateful operation, so a stateful operation in streaming,
So in a real-time warehouse you're talking, right? Let's say I got the transaction now in one table, and I got the another transaction in 2 days back. So I'm linking these two tables in a warehouse and doing a transformation. So how can I get the 2 days back data if you're doing a real-time warehouse?
so basically you're saying I mean, it really depends on the use case. If it's CDC and you have data that's late, that's fine, right? Because the sequence by that apply changes into gives you ensures that even if data is out of order, that the latest data that the system has seen so far will always be the one that's presentable to the user. So in Scd Type 2, we're going to resolve that in the right order as well. Okay, so a lot of thinking about how do we handle late arriving data without having to fiddle with watermarks. And to be clear, there still is watermarks in DLT, right? We're not getting rid of the whole, like there are, physically speaking, you still have to use watermarks sometimes when you're doing microbatch stateful processing. But apply changes into and merges give you ways to compensate for late arriving data. Like you could have data that's late by a week, maybe even a month, but that sequence by and apply changes into or how you're writing your merge statement is going to make sure that the system doesn't, you don't have to, really overthink it or the system's going to show it out of order.
To elaborate a little bit more on that, the capability of the Scd Type 2, which is in preview now, okay, but that capability can even handle, for example, the deduplication within the batch itself, okay? So traditional notebooks, you'd have to handle that deduplication. You use the Scd Type 2, apply changes into, you tell it to sequence by, and it doesn't matter whether it's a single batch that has duplicates, multiple batches, it handles it, and then when you get that late arriving data, it natively handles that.
All right, thanks everyone. We are at time. We have to set up for the next session. Maybe our speakers would be out in the hall if people want to ask more questions. Thanks everyone.